Hello, everyone, and welcome to part 3 of Modeling and Optimization Word Problems. We're starting with number 10. A cylindrical can is constructed using 100 square inches of tin. This amount also includes a top and a bottom for the can. What is the largest volume? I see it. There's what I'm trying to maximize or minimize. So step 1 is to write the equation for the thing that you are trying to maximize or minimize. So we're talking about a cylindrical can. So it is your job to know that the volume of a cylinder is pi r squared, which represents the bottom disk, times h. So if you repeated disk, you would have a volume. So that's what we're trying to maximize or minimize. Obviously, we could just make the radius and the height a gazillion and we'd have a huge volume. But we're being constrained by the fact that we only have 100 square inches of tin. So your job is to know that material is always going to be related to surface area. Your construction material is going to be related to your surface area. So the surface area of a cylinder is you have the bottom and the top, which are both circles, so pi r squared, and there's two of them. And then you have the lateral surface area. So you have a circle that continues all the way down. So pi r squared, or not pi r squared, 2 pi r, which is the circumference, and then times h. So in this case, we have 100 square inches of tin, and we need to cover the entire surface area. The purpose of the constraint is to reduce the volume equation, or equation number 1, in this case volume, to one variable. So the thing that I can get alone the easiest is the h, which is good because then I won't have to square it. So 100 minus 2 pi r squared is equal to 2 pi r h divided by 2 pi r divided by 2 pi r. And so h is equal to 100 minus 2 pi. Now, be really careful. It is so tempting to cancel this 2 pi and one of these r's, but that 100 prevents you from doing that. It's subtraction on the top. It would be like saying 5 minus 3 over 3, which we know to be 2/3. It'd be like saying, oh, it's 5. It's not 5. Don't cancel them. Can't do it. So now I can use that h to rewrite equation number 1. The volume is pi r squared times 100 minus 2 pi r squared over 2 pi r. Yes, you could have simplified that a little bit. I'm just waiting until this step because I had the foreknowledge to know that the pi's would already cancel. And then now this r is being multiplied by this whole thing, and this r is dividing into that whole thing, so those r's can be canceled. Not these two, but this one on the outside that's multiplying the entire thing. So now I'm going to distribute that r to the whole thing, 100 r minus 2 pi r cubed. And this too, I always tell people the safest way to handle a denominator is to put it separately. When you do it separately, you have such a better chance of simplifying it correctly. So your volume is 50r minus pi r cubed. Step 4 is to take the derivative. Again, I have to do it at least once today, you know that. So this is some kind of a negative cubic equation. It ends down. It definitely goes through 0, 0. So let's just say it looks like this. I don't actually know what it looks like, but I do know that there is an r value. So this is r, different values of r are creating different volumes. And obviously a 0r creates a 0 volume. But a 1r, so if you made r just 1 and made this really tall, you would get a volume, but it wouldn't be as good as whatever r this is. So we're trying to figure out what r creates this volume right here, this maximum. And what do we know about that point on the graph? we know that its derivative right there is 0. So there's lots of different slopes along the graph, but that point can be found by saying the derivative is equal to 0. So let's find the derivative. 50 minus 3 pi r squared. I set the derivative equal to 0. And I solve. 3 pi r squared is equal to 50. R squared is equal to 50 over 3 pi. Now, if you were in the classroom, I would totally make you do this on your calculator to see if you could do it correctly. You're not here, so I can't really force you to do it. I know you're just going to wait for me. But I will tell you that the first time a kid made this mistake, I must have spent a half an hour looking for it on a test. So I personally have never forgotten it. And that is that if you do on your calculator square root of 50 divided by 3 pi, I know in your eyes that pi just looks connected to that 50 over 3, but it is not. It is going to do order of operations. So your calculator is going to do 50 divided by 3, and then it's going to multiply by pi. It does not think that that pi is in the denominator. So your two choices are either to use that fraction power that your calculator has to actually write this as the square root, and then use the green F1 to create the two little boxes and actually fill them in. Or you can do it this way and use parentheses. But if you get the wrong answer, so if you type into your calculator and you get 7.236, that means that you did 50 over 3 pi without putting the pi in parentheses. So this is my warning. If you make this mistake, I will take off half the points of this problem, even though it should be a 1-point error, because you have been warned. Okay, so the correct answer is 2.303. Although you're going to want to leave it this way, you don't want to use your rounded answer to find the other things. Okay? Don't use the rounded answer to finish. So since you have the square root of 50 over 3 pi, you must have typed that in your calculator to get to the 2.303. So whatever the complete number is, 2.303, blah, 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 hit store as X. And once you store it, then you're capable of going back and finding the volume. What is the largest volume? You can say the volume is, remember, you've already put it in terms of R. You don't have to go back and find H. You have the volume in terms of R. 50x on your calculator, because you've stored that big long R as X, minus pi x cubed. And if you do it that way, you will get the exact answer. If you are wrong, even a thousandth of a number, you're going to get the problem wrong. And that would be such a shame if you knew how to do this one. So make sure that you're exact. This is the largest volume. So step 6, make sure you know what you're finding. Step 7, make sure you have the units. Radius would just be inches. Height would just be inches. Surface area would be square inches, and volumes are cubes. All right, let's do number 11. Determine the dimensions of a right circular cylinder of maximum, here it is, lateral surface area that can be inscribed in a sphere. Oh, this is fantastic. All right, so let's draw our sphere, which I know it just looks like a circle, but I don't know how to draw a sphere, three-dimensional. So I'm going to stick a cylinder in it. Inscribed means that it touches. It's going all the way to the edges of the sphere, not just like floating around somewhere in the middle. That's not inscribed. So of course, this is just one way to draw it. Another way to draw it. So I'm going to try and draw 3 identical spheres so that you understand this concept. I could draw it like this. This would still be considered inscribed as long as the edges of the cylinder are touching the sphere, or I could draw it really wide and fat. We did this yesterday with another problem. There's my cylinder. It's touching. You can't quite tell. So we're trying to maximize the lateral surface area. So step one, what is the lateral surface area of the sphere? I'm not going to do LSA, just area of the sphere. So remember on the problem that we just did, lateral surface area is just the one that goes around. So like a toilet paper roll that has no top or bottom, that would be the lateral surface area. So that would just be the 2 pi r, the circumference, times the height. You don't need the pi r squared top, and you don't need the pi r squared bottom. So it's just going to be 2 pi r h. Now let's do the constraint. This is the hard part. So because it's inscribed in a sphere, here is the center. It is going to be even on the top and the bottom. Here's the question. Draw the radius of the sphere on your paper. Are you waiting for me? No, you draw it. Okay. Did you draw it like that? I bet at least half of you did. That is the radius of the sphere, but it doesn't help us with the problem. So instead, the key to this problem is drawing the radius to the corner of the cylinder. That's also the radius, but that's also part of the problem, where this radius is not. Okay? All right, so I'm doing all 3 pictures because I want you to see how it works. So I'm going to make a right triangle. This is the key to this problem. This dimension represents the radius of my cylinder. This represents the height of the cylinder divided by 2 because it actually goes all the way up to the top. And then this represents the radius of the sphere, which we know to be 8. And now we have our constraint. So again, this would be the radius of the cylinder. This would be half the height of the cylinder. And this would be 8. So even though they all are different, it still produces the same equation. This is just half of the height. Now we have to make a decision. If you do this now, you're going to get h over 2 squared plus r squared is equal to 8 squared. You can do that. Or you could just call this x. X squared plus r squared is equal to 8 squared. But then when you were all done and it said find the dimensions of the cylinder, you would have to remember that the dimensions, the height is actually going to be twice x. But at least you would be doing the whole problem without a fraction, which could be nice. So here it's 2 pi r. Since we no longer are using the h, what are we going to replace h with? 2x, right? X, it would take 2 x's to make the height. So if you wanted to do it this way, well, this is how I'm going to do it. 2 pi r 2x, which is 4 pi rx. I personally think it's better not to use the fraction, so I kind of like that. But you should do what you want. You can skip ahead. I'll just tell you the answer. The radius is 4 square roots of 2, and the height is 8 square roots of 2. So if you want to see if you can finish it on your own, then you can do that. So x is equal to the square root. That square's a little lost there next to my page 90, but notice it is 64 minus r squared. So now the purpose of the constraint is to reduce the equation that you're trying to maximize or minimize to one variable. So I'm going to change it to 4 pi r x. So before I change that to x, I'm actually just going to do one more thing. 64 minus r squared to the 1/2. because we can't take a derivative with a square root. We need to change it to a fractional exponent. Step 4, so I'm going to start back up at the top here. Step 4 is to take the derivative. So I personally am going to exclude the 4 pi. It's a constant. That way I can just do product rule with the r and the 64 minus r squared, rather than making one of them 4 pi r. So the second times the derivative of the first plus the first times the derivative of the second. This one's a pretty tough derivative. I bring down the 1/2. I write 64 minus r squared to the negative 1/2. And I still have to do the derivative of the inside, negative 2r. A lot going on there. So you may remember from derivatives B, my insistence that you learn how to factor out of this. This is why, literally. You have 2 parts, and you need it. We're eventually going to set this equation equal to 0, so we need it factored. So the 4 and the pi are already factored out. And now, of the 1/2 and the negative 1/2, the negative 1/2 is smaller. So that's what's going to come out. And since this just has a 1, there's nothing left to take out. In the first one, remember, it's always going to be to the first power that's left if you've done it right. So if I write it as to the first power, negative 1/2 plus 1 is 1/2. So that worked. Little quick simplification here before I continue. The 1/2 and the 2 cancel. And then I have an r times a negative r gives me negative r squared. So there should still be 2 parts. This is the part that sometimes people mess up. If originally you had 2 things and you're factoring out, you should still have 2 things. This negative r squared is not being multiplied, it's being subtracted. So my derivative of my area is 4 pi. I'm going to change this back to parentheses now because I'm going to simplify it. 64 minus 2r squared over the square root, just an easier notation. And now that I'm done with my derivative, I can move it back. Step 5, we've taken the derivative. We're going to set it equal to 0. I'm just going to erase this. We all know that. And I'm going to clear my fraction by multiplying both sides by 64 minus r squared, square root of 64 minus r squared. That gives me 0 is equal to 4 pi times, if you want to take out the 2, you can, but you don't really need to. So either 4 is equal to 0, which it's not, or pi is equal to 0, which it's not, or 64 minus 2r squared is equal to 0, which must be what it is. So since I didn't take out the 2, I just have a little extra step here to divide by 2. And I'm going to square root both sides. Now, technically, the answer is plus or minus. I don't want you to forget that. But in this case, it's a radius, so we're only going to consider the plus answer. I break it down into parts I can do and parts I can't. And I get 4 square roots of 2, which is the answer. Now, be careful. The question asked for the height. But in our equation, we got rid of the h, and we have an x instead. So I'm going to take my r and plug it in here to find x. 64 minus r squared. So r squared was 32. So I get h is equal to, not h, sorry, x still. So x is equal to the square root of 32, which, like this square root of 32, is 4 square roots of 2. But x is just this distance. It's only half the height of the cylinder. So h is equal to 8 square roots of 2. So my final answer, I'm just going to have to tuck it in here in the middle of the page, is that r is equal to 4 square roots of 2. Some people write units because they want to make sure they never forget their units. But when it's just units, you don't need them. And h is equal to 8 square roots of 2. So pretty challenging problem. Again, you don't have to, you can just leave it h over 2 if you don't want to introduce the x, but I thought it was easier that way. All right, let's do number 12. You are designing a poster containing 50 square inches of printing with margins of 4 inches at the top and bottom and 2 inches at each side. Whenever you can, draw a picture. So I have this printed section, and then I have my margins of 4 inches at the top and the bottom. So this distance right here is 4. So do something to indicate the 4. And then this distance right here is 2 on each side. I did not draw it to scale. I didn't even draw it very neatly. It's okay, but I drew it. That's what I really want, is for you to draw it. Find the overall dimensions that will minimize the amount of paper used. So this used to be on the homework and people struggled with it a lot. So I decided to just do it for you. The main problem was that people made the overall dimensions X and Y, which is fine. That's not wrong. But the problem is just so much easier if you let the interior dimensions be X and Y, and then let the outer dimensions, I don't know why I did that, and then let the outer dimensions be y plus 8, because it's this distance y, and then there's a 4 on either end. And this dimension, the outer dimension, is going to be x plus the 2 plus the 2, which is 4. That will make your life easier, because it says that it contains 50 square inches of printing. So this space right here is 50. In other words, x times y is equal to 50. That's our constraint. So the overall dimensions that will minimize the amount of paper used. So we want to use, paper would be area, kind of like I talked about back here where I said material usually equals area. So you're talking about paper. Again, the paper, amount of paper, it's going to be an area. So your total area for the whole page is going to be x plus 4 times y plus 8. This is what you're trying to minimize or maximize. You might want to simplify that a little bit. First, outer, inner, last. Something went wrong. 8x. So this one does have just a little bit of a trick to it, and that is that xy is equal to 50. So I can actually change this to 50 plus 8x plus 4y plus 32. Notice I'm still calling it a. I haven't taken a derivative yet. 8x plus 4y plus 82. So this is the equation that I want to maximize or minimize, but it has two variables. But fortunately, I have a constraint. So I'm going to get one of the variables alone. It doesn't matter which one you do. So y is equal to 50 times x to the negative 1. So 8x plus 4 times 50x to the negative 1 plus 82. Area is equal to 8x plus 200x to the negative 1 plus 82. Finally, this is why it's so important to label your steps. So far, I haven't done any calculus, but now I'm going to. So what this is saying is this graph, whatever it looks like, right? I don't know what it looks like, but the x will tell you the amount of paper. So I want to minimize it. I want to find the x that reduces the amount of paper. But whether I'm maximizing or minimizing, I'm still finding the point where the derivative is equal to 0. So the derivative is 8 minus 200 x to the negative 2 plus 0. Going backwards today. Sorry about that if that was confusing. So I set it equal to 0, and I get 8 minus 200 over x squared Personally, I clear the fractions. Or you can add 200 over x squared first. Either way. 0 is equal to 8x squared minus 200. So at some point, you're going to have to, move that 200 anyway. 8x squared, divide by 8, divide by 8. Sorry, I don't know what it is off the top of my head. 200 divided by 8 is, oh, maybe I did know what that was, 25. So x is equal to 5. So be careful. The question is, find the overall dimensions. So what you found was this dimension right here. This dimension is going to be 5. And because xy is equal to 50, the y is going to be 10. And when you see something like this on a quiz or a test, the answer is not 5 by 10. The overall dimensions will be 5 plus 4, 9 by, and then this is going to be 10 plus 8. It's 9 by 18. So it's 9 by 18 inches. All right. Next one, number 13. A field of rectangular shape is to be fenced off along the river. No fence is required on the side lying along the river. If the material for the fence costs $2 per linear foot and the two ends are $3 per linear foot for the side parallel to the river, find the dimensions of the field of maximum area, I see what they're asking me to maximize, that can be enclosed with $900 worth of fence. So that can be, this is going to imply my constraint. So first, I'm trying to maximize or minimize the area. So that's going to be my main equation. Oh, let's draw it. So I've got a river. I've got fencing. The two ends cost $2 per foot, linear foot. It's not area. $2 per linear foot. And then this side, for whatever reason, is more expensive. Must be a different kind of fencing. $3 per foot. And let's just call these x and y. Obviously, x is the same. So the area is going to be just x times y. The area doesn't change just because it doesn't have a fence along that side. I'm being constrained by money, but there's actually like a dual constraint because the money is dependent on the perimeter. So the perimeter is 2x's plus y. But what you really want for your constraint is the cost. So the cost is going to be $2 for all this footage, which is 2x. And then it's going to be $3 for all this footage, which is y. So your cost can only be $900. This is your constraint. So I know some of you are still putting your steps in, and that's okay. 900 is equal to 4x plus 3y. All right, we'll move a little faster on this one. So the purpose of the constraint is to reduce the main equation to only one variable. It doesn't matter. It's just x times y. It doesn't matter which one you get rid of. So let's do 900 minus 4x is equal to 3y. Y is equal to 300 minus 4/3 x. That means I can now rewrite my area formula as x times 300 minus 4/3 x. You could use product rule, but I think it's easier to do 300x minus 4/3 x squared. Step 4, take the derivative. The derivative of the area equation that we found is 300 minus 8/3 x. I set the area equal to 0 as my step 5. Sorry, the derivative of the area equal to 0. 8/3 x So 8/3 x is equal to 300 times 3/8 on both sides. So 300 divided by 8 is equal to 37.5. So x is equal to times 3, 112.5. And what did that find us? It found us this distance right there. What do they want to know? Remember, step 6 is actually answering the question. Find the dimensions of the field. Okay, so we found one dimension. So I now need to know y. I go back over until I find it. So y is going to be 300 minus 4/3 of the 112.5. So times 4/3, it's going to be 150. Final step is to add the units. 112.5 by 150 feet. Those are the dimensions that you're going to want. So this one, the derivative, piece of cake, the solving, so great. This is the hard part, that it kind of had a double constraint. Technically, the constraint is the cost, but in order to do the cost, you need to know the perimeter. Okay, so the last one is number 14. If you are in honors and you'd like to call it a day, you can be done. If you want to put this in your notes in case you need it for college, you're welcome to follow along for number 13. But I will not put one like 14. I will not put one like 14 on your homework or on a quiz. So number 14 says that a man in a boat at a location 5 miles from the nearest point on a straight beach wishes to reach a place 5 miles along the shore from that point in the shortest possible time. If he can row at a rate of 4 miles an hour and run at a rate of 6 miles per hour, where should he land? So let's try and draw a picture of this. Here's our beach. Here's our little man in the boat. So it's 5 miles from the shore if he goes to the nearest possible point. But he actually wants to go to a place that is 5 miles north of his point, or 5 miles away from that point on the shore. So the question is, where should he land? Meaning, he could just row straight there. But as you can see, he can only row at a rate of 4 miles an hour, but he can run at 6. But that doesn't necessarily mean he wants to row straight in and then run. He's probably going to split the difference somehow. So maybe he's going to go to there and then run the rest of the way. Our job is to figure out which one of those choices is the fastest. So I'm just going to go ahead and put it right there because we don't actually know the answer. But somewhere they want to know where he lands on the beach. Where should he land? So right here, should he go a mile up from where he was, or 2 miles, or 3, or all 5? So in order to do this problem, the main thing that people have trouble with is remembering this equation. Distance is equal to rate times time. Distance is equal to rate times time. It's classic, gotta know it. So we're trying to minimize his time, shortest possible time. Well, where's his time going to come from? It's going to come from his time in the boat plus his time running. So if distance is rate times time, then time is distance over rate. So I'm just calling it m because it's what I'm going to minimize. So his time in the boat would be his distance in the boat over his rate in the boat. His time running is going to be the distance that he runs over his rate running. Well, I know that his time in the boat when he's rowing, his rate is 4. When he's running, his rate is 6. His distance in the boat is going to be this green distance right there. What is that? Well, it's going to be if the square root of x squared plus 5 squared, because it's a Pythagorean triangle. So x squared plus 25. And what is his distance running? It's going to be this distance, which isn't part of a triangle, but since the entire distance from here to, bad to use it next, from here to here is 5, right? Then this distance right here is 5 minus x. This is the equation that I want to minimize. I'm just going to change it slightly. I want to change this to x squared plus 25 to the 1/2. And I'm going to change this to 1/6 times 5 minus x, because I don't want you to think you need product rule, or power quotient rule, because there's a 6 on the bottom. It's just a constant out in front. So let's take the derivative. The derivative is 1/8 times x squared plus 25 to the negative 1/2 times 2x, derivative of the inside, plus 1/6, can just stay there. And this isn't, it's not to the, it is to the first power, but we're not going to do it that way. In fact, if you want, you can think of it as this, if it helps you, minus 1/6x. But the derivative of the inside is just -1. So -1. So in other words, it comes out to -1/6. So I take the derivative and I set it equal to 0. 0 is equal to 1 over, not 1, 2x over 8 times x squared plus 25 to the 1/2 minus 1/6. So you can clear the fraction first, or you can just move the 1/6 over, up to you. X over 4 square roots of x squared plus 25. You can use whichever notation makes you comfortable, but I am going to reduce the 2 and the 8. So I am going to clear the fraction. Could have done it in the step before, doesn't matter. Multiply both sides by 6. And actually, do you see that I can multiply both sides by 12? It is just a little easier, and I feel like I should show you that. 12 square roots of x squared plus 25. 12 and the square root of x squared plus 25. So the 12 and the 6 cancel and leave you with 2 square roots of x squared plus 25. And on this side, that cancels, and this leaves you with 3x. Now I square both sides, and I get 4, careful, the 2 actually squares, and the square root cancels, is equal to 9x squared. 4x squared plus 100 is equal to 9x squared, which is 5x squared is equal to 100. X squared is equal to 20. And so x is equal to plus or minus the square root of 20, but again, it's a distance. So we only need the positive value. Now, normally I would say you could leave your answer as a square root. It simplifies to 2 square roots of 5, but that's not really very helpful in terms of miles. Like, how far should he run? He should run 2 square roots of 5 miles. That's a little silly. So I'm just going to quick do square root of 20 on my calculator, and I get 4.472. 4.472. So that's this distance right there. So he should land 4.472 miles above the nearest point. So this is the nearest point, but he doesn't actually want to go there. Do you guys see how close that is to 5? So literally, he is actually, like, if this was really the triangle, here's 5, here's 5. He's going to row in almost the whole way. 4.472 miles. And then he's only going to have to run just a little bit. All right, that is it for modeling and optimization. So there is a very long packet of problems. This is going to be a 50-point quiz. It'll be 5 questions that all come directly from the packet, just with the numbers changed. If you do the packet, you should be able to get 100 on it. All right, have a great day.